All right, welcome everybody to graphing reciprocal trig functions. What we're going to basically do here is look into the graphs of the cosecant, the secant, and the cotangent function, and basically kind of relate them to their reciprocals of sine, cosine, tangent. And in our last unit, we looked at graphing the sine, cosine, tangent, kind of based off of the unit circle, and that's what I kind of devised from here. I mean, obviously my class, to save some time, we just kind of used some technology, which I will kind of use the technology component as well. But also, when we have a little bit more time, I also like for students to kind of investigate, kind of see where this graph shows up, not just to assume that, oh, these are the points. So what we're going to do is kind of similar to what I did in the last warm-up for the graphing sine, cosine, tangent, is we are going to graph these, graph the reciprocal functions based on the points on the unit circle. Now, I am going to start using some patterns. And when we did this last section, that's what I advise my students to do. Rather than like plugging in these points for each and every one, I wanted them to start seeing some patterns. And I didn't go over the patterns with you guys in there just because, kind of for like a little bit of time, I wanted to kind of do this, kind of revise, do some work, review on the unit circle. But now that we have a good sense of the unit circle and evaluating these points, we're going to look at some kind of tricks to help us evaluate these points and on a graph much sooner, much quicker than we previously did. So just remember, here's our axis here. Now this is where it's going to be 0, and we are going to evaluate here for all of these points. So I'm going to do pi over 6, pi over 4. Now in this case, since I'm going to be kind of skipping around, I'm going to want to actually, I'm going to write all of these in now because it's just going to be a little bit easier to find the points as I kind of move forward. Now, one thing that is also kind of important to remember on this, these are the angles that are on the unit circle. And when we look into graphing our trigonometric functions, when we get a smooth curve, what that's doing is that's representing all the possible angles that we could evaluate. And we are limited with what angles we can use based on the unit circle and special right triangles. So that's why we are just plotting the points to kind of like understand what the curve is going to, curve of the graph is going to look like. But when we fill it in, obviously what we're doing is we're taking into consideration all of the angles that make up the graph. So that is a nice little introduction. So now let's go and think about what is it we understand? And if we, to kind of go back, to kind of do a quick little review of the sine graph, we had a maximum at pi halves, or the initial period, because in this warm-up, before we get to actually doing everything else, we want to talk about the, we want to talk about, investigate where to get this from, where the cosecant graph is going to be coming from. And remember, the cosecant is the reciprocal of sine, right? Sine from triangles was opposite over hypotenuse, and therefore cosecant was hypotenuse over opposite. In terms of the unit circle, sine represented the y coordinate point on the unit circle, where cosecant represents 1 over y. But what we did last kind of lesson is we looked into graphing the sine function, and we came up with a curve that kind of looked something like this. So I'm actually going to have to do this all in one swoop. And hopefully it's going to look. Now, obviously you can see that I have, there you go. All right, now eventually I'm going to take that away. But that is the sine graph. And I'm just going to write, y equals, and let's put it, do I have any more room? No. Let's put that as y equals sine of x. Okay, so that's the y equals sine of x function. Actually, I'll just write up here. Y equals sine of x. Okay, so that's the sine of x function, and we are tasked to graph the cosecant. Now, looking at their relationship, we know that they are the reciprocal. So let's go back up to the unit circle and kind of make sense of these points so we can kind of quickly fill in the points from the unit circle. So we have our first quadrant, which we used last class period. And now what we're going to do is we're actually going to use the whole unit circle here to kind of make up our points. Now, we are going to come back to the first quadrant here in a second. But for right now, I just want to look at these coordinate points, because these coordinate points are very important for us understanding the reciprocal trigonometric functions. And they're very easy to remember. And a lot of students, they have trouble when we start talking about where the what what the graphs look like and where there are certain values of the trigonometric functions. And one thing I always remind them is to use these coordinate points from the unit circle. So remember, the sine represented the y coordinate, right? And let's just go and check our work. At sine of 0, we have 0. At the angle pi halves, sine of pi halves is 1. We got pi halves is 1. At pi, 0. At 3 pi over 2, sine is equal to negative 1. And then at 2 pi, we're back at 0, all right? Now let's look at that reciprocal relationship. So if we know that the sine of x represented the y coordinate, then the cosecant of x is the reciprocal, so that's 1 over y. So at this first point, we have 1 over 0. Well, that's undefined, right? So what that means is undefined values, what we talked about in functions, that's going to be represented as a asymptote. So that's going to be a discontinuity in the graph. Now let's go to our next angle, pi halves. When we do 1 over 1 here, we're just going to get 1. So that is a shared point. When we go to pi, the angle pi, that's again 1 over 0. That's an undefined value. So again, we're having an asymptote at pi. And then when we go to 3 pi over 2, you can see that that is 1 over negative 1. So that's going to be at 3 pi over 2. We have a shared point. And then at 2 pi, it's going to take us back to 1 over 0. So that's going to be another vertical asymptote. So the first thing that I notice about these reciprocal functions, if it's, cosecant or secant, anytime we're going to be taking the reciprocal of 1 over 0, it's going to be undefined. So these functions are discontinuous, like the tangent function. And the same thing, even with cotangent, cotangent would be x over y. That's going to be x over y. You're going to have discontinuity. So sine and cosine are trigonometric functions that are continuous, whereas the other trigonometric functions are going to be discontinuous. Now, as far as the coordinate points, rather than plugging in each and every one of these points like I did last time, let's kind of start looking at some patterns. So if we look at the first one, I'm going to zoom in here so I can kind of write this in. So this first angle, remember, was pi over 6. Okay, and that coordinate point was square root of 3 over 2, comma 1/2. All right. Oh, that's not a really good scale, is it? Let's put 2 right here. Oh, I wanted that to be, 1.5, whatever. I guess I'll do that as 2. Okay. So that is the coordinate point for pi over 6. So when I go to evaluate, pi over 6 for the cosecant, that's going to be 1 over 1/2. So if I take 1 over 1/2, multiply by the reciprocal, let's do this in purple, I get 2. So at pi over 6, I have a coordinate point of 2, which we'll place like right there. Now, rather than just like stopping there and moving to pi over 4, let's look at where all the other points where I'm going to be 1 over y, where y is equal to 1/2. And what that does is that looks into us as the reference angle, because remember, this angle has the same reference angle as the same value. So all these other points here in these other quadrants, pi over 6, that all have the same reference angle, are all going to have the same coordinate point. Right? It's just a reflection. This coordinate point over here is going to be negative square root of 3 over 2, comma 1/2. This coordinate point is the same one, negative square root of 3 over 2, comma negative 1/2. And then this one over here is square root of 3 over 2, comma negative 1/2. So they all have the value of 1/2. It just depends on which quadrant the angle is in, if it's positive or negative. And then now we basically need to determine, well, what are all these angles then? They all have the same reference angle as pi over 6. And if you look at them, they're all going to be the angles that have 6 in the denominator. 5 pi over 6 has a reference angle of pi over 6. 7 pi over 6 has the reference angle of pi over 6. And then 11 pi over 6 has a reference angle of pi over 6. So what I'm going to do is I'm going to quickly plot the rest of these angles. So we have 5 pi over 6. The y coordinate is positive, so therefore that is also a 2. Then I look at 7 pi over 6. 7 pi over 6 is in the third quadrant, so that's going to be a negative 2. Let's move the 2 right there. Change that. I want to make sure at least my scale is okay. So I'll make that a negative 2. And then 11 pi over 6 is again in the fourth quadrant, so that's going to be a negative 2. And now we can move on to the pi over the next angle. So the next angle is obviously going to be at pi over 4. And that coordinate point is, again, square root of 2 over 2, comma, square root of 2 over 2. Let's move that. All right. And so therefore, if I was going to reciprocate with that angle, or if I was going to evaluate what that would be, I would have 1 over square root of 2 over 2. And when I go ahead and reciprocate, multiply by the reciprocal, on the top and the bottom, I'm just left with 2 over the square root of 2, rationalize the denominator, and I get just the square root of 2. Now, I don't know what the square root of 2 is. I could approximate that, but in this work, I provided the square root of 2 is 1.41. So for pi over 4, I'm at 1.41. So that's going to be somewhere, in the middle there. Oh, let's go back to purple. Now again, I can look at what are all the other angles that have pi over 4 as the same reference angle. Well, again, those are going to be all the angles with 3 pi over 4 has a reference angle of pi over 4. Same coordinate point, but in the second quadrant. 5 pi over 4 has the same reference angle as has a reference angle of pi over 4, but it's in the third quadrant. And then 7 pi over 4 has a reference angle of pi over 4, same coordinate point, but it's in the fourth quadrant. So again, we're dealing with this 3 pi over 4 is going to be 1.41 positive. And then we'll get into, where's my 7 pi 6? Oh, I wrote that down wrong. That should be 7 pi 6. That's 5 pi over 4. So I messed that up. That should be a 5 pi over 4. So that is going to be a negative 1.4. And then we have 7 pi over 4, which is a negative 1.4. And so now you're starting to see kind of like this relationship, this kind of shape that's coming through. And then we can add this up. Let's do the last one, which is the pi over 3. So again, looking at that, if we look at this coordinate point, which is from there to there, which is pi over 3, which again, that coordinate point is 1/2, comma, square root of 3 over 2. So if I took 1 over the square root of 3 over 2, which basically reciprocate that to 2 over the square root of 3, and when I rationalize the denominator, I get 2 square root of 3 over 3, which I have that approximated as 1.15. And again, the only angles that have the same reference angle are going to be with the 3 in the denominator here. So pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So those are all going to be at 1.15. So let's just go and plot those. Pi over 3 is in the first quadrant, so that's 1.15 positive. 2 pi over 3 is in the second quadrant, so y is positive. Then let's go to 4 pi over 3, which is in the third quadrant, so the y is negative. And 7 pi over 3, that's 5 pi over 3. Again, messing that up. And that is going to be a negative 1.5 because that's in the fourth quadrant. So hopefully you can see there. Now we kind of have this shape. It looks kind of look like a parabola. And I'm going to try to do my best here. And if we just kind of like connect these to represent all the angles that we could have used, rather than just the angles that we know the values of on the unit circle, what you'll see is we're kind of getting like this mirrored image of these kind of like parabola kind of shaped figures. Right? So you can see it's kind of like the mirror image. And then again, that kind of plays into like the reciprocal functions, right? It's like the flipped image of that graph. The important thing to understand here is, again, that we're going to have these asymptotes. And again, these are functions. You can see that it's changing from when sine was increasing, cosecant is decreasing. When sine is decreasing, cosecant on this interval is increasing. Here it's decreasing, here it's increasing. Sine is increasing, cosecant is decreasing. So you can kind of see how it's playing like this alternate form of the reciprocal function. Now, again, we're not including the sine as part of our graph. We're just looking at the purple, which is the cosecant function. But the main important thing is identifying not only the points, but looking at these quadrants where you can come up with this graph. And you could do the same thing for secant. You could do the same thing for the cotangent to evaluate them. But for the rest of them, I'm just going to kind of provide you with those answers. And So yeah, so that's basically that. You can see this is our initial period of the cosecant function. What's also important to kind of recognize is that this is considered one period. So for one period, you're going to have kind of these opening here and these asymptotes breaking it up. And now what we're just going to kind of get into is looking into the transformations of cosecant, secant, and cotangent. And what I also wanted to do was provide you with a kind of a Desmos version so you can kind of see how these graphs kind of relate. Because again, this is just this is just our initial period. This is one section of the graph. So when we go ahead and take a look at the Desmos version, which I'll bring over here. Okay. Again, you can see this relationship. So here's the sine graph, right? And we just did the initial period from 0 to 2 pi. Now, again, when we look into the cosecant, right, you can see that every single time where the sine graph had an x-intercept, that obviously the reciprocal is now going to be undefined. So there's a vertical asymptote that obviously Desmos is not providing. You can see these shared points that they are occurring. And the same relationship happens with cosine and secant. So we can go and take a look at cosine, and then we can look at the secant graph. And again, it's just that reciprocal relationship we are getting with our points. And tangent and cotangent don't have the same love, but you can see they're very much related to each other. There's some transformations that are applying to them. And obviously, if you remember where tangent is going to be 0, cotangent is going to be undefined. Where cotangent is equal to 0, tangent is going to be undefined. And again, that comes to those 4 points that we talked about at the unit circle. And that's why I like to start with that warm up so you guys, can kind of really better understand what's going on. So that's basically just the transformations. Again, when we looked at the, f of x equals a times f of b times x minus c. Plus, let's raise that. Plus d. Again, these go through the transformation. So again, it doesn't matter what our function is, if it's a square root, a cube root, a radical, a reciprocal function, a logarithm, an exponential, the a, b, c, and d are going to apply the same operations. A is going to be vertically stretching or compressing the graph, reflecting about the x-axis. B is horizontally stretching or compressing the graph, or reflecting about the y-axis. C is shifting the graph left or right, and D is shifting the graph up or down. And the main important thing to kind of look at is that the, I don't know what I was actually going to say with that. So let's go and take a look at, let's kind of just revise these with the initial period here as far as talking about the characteristics of the cosecant and secant. And I don't know why I left that on there, but that is wrong. That is one thing that I make sure I tell my students. I guess I just forgot to erase that when I copied it from the last notes. But there is no amplitude for cosecant and secant. Amplitude, remember, is the half distance from the max to the min of a graph. So sine and cosine are bounded functions. They have a absolute maximum and an absolute minimum, so they're bounded. Whereas where cosecant, secant, tangent, and cotangent do not have an absolute maximum or an absolute minimum, so there is no amplitude, all right? The period for cosecant and secant is just like the sine and cosine. It's going to be 2 pi over b. The phase shift is, again, going to be equal to c. Vertical shift is going to be d, and then domain range. So let's go and talk about our initial period. So we already did the initial period of the cosecant graph, but let's just kind of like put it back on another thing that we can kind of copy down. So we know it's going to go to 2 pi. And the way that I like to kind of write that initial period is just to draw, sorry, the sine graph first. So just to kind of get an idea of how we're going to look, it's basically, here's the sine graph. So then the cosecant graph is going to have a vertical asymptote at here, here, and here. And then we're just going to have some reflecting arrows there. So we can very quickly go to graph. Now, obviously, we can remove the sine graph. I'm just going to leave it in there so you can see how that graph plays in with the cosecant graph. But the black graph is going to be our cosecant graph. So that is going to be y equals cosecant of x is in black, and the purple is my y equals sine of x. All right. So that is going to be for the cosecant graph. And if I wanted to find the initial period for the secant graph, I would do the exact same thing. Just go ahead and create here. Let's go ahead and draw from 0 to 2 pi. And there. So it's going to start again at 1. Let's go down to -1. And so we'll just kind of go from here up and down from there. Now, again, you can see in this initial period, we have 2 intercepts. So that's where my asymptotes are going to go. All right. And then my curve is going to look a little bit broken up, kind of, because we're only going to see 1 full curve here and the rest go. But again, as we looked in that last graph, these graphs, obviously continue. This is just one initial period that we are looking at. So the main thing when we're looking at, the cosecant and secant, what we're really going to be concerned about is that is incorrect. Man, I need to rewrite this. That is not the domain. That is not the range. The x scale is going to, again, be helpful for the period, phase shift, and everything else. What we want to do is be able to identify the asymptotes because as well as the range. So let's go ahead and take a look at, I don't know where the -a plus k came from. Sorry about that. So the main important thing when we're looking at cosecant and secant is identifying the asymptotes. And again, the asymptotes come from when the cosecant graph is undefined. And the cosecant graph is undefined here when sine is 0. And within this initial period, you can see that sine is equal to 0 at 0, pi, and 2 pi. And actually, let's kind of go back up to the unit circle here to kind of understand this. So here's our point 1, 0. Here's our point 0, 1, -1, 0, and 0, -1. All right. So if we're talking about sine, that represents the y coordinate, right? Sine of theta equals the y coordinate, and cosecant of theta equals 1 over y. So if we're looking for whenever y is equal to 0, we know the cosecant is going to be undefined because you'll have 1 over 0. So therefore, an asymptote is going to occur. So you can see that the first asymptote occurs at 0, the angle 0, and then it occurs at pi. And then it would occur at 2 pi, and then it would occur at 3 pi, and then it would occur at 4 pi, 5 pi, 6 pi, 7 pi. And you can see that each and every time, you're just adding pi to it. So when we want to find the asymptote, what we need to do is just usually choose the smallest positive asymptote that we have. And even though 0 is not positive or negative, we can set this up as far as saying, and let me write this in for cosecant. Okay, so we can say x equals 0 is my first smallest asymptote that I can record, at least in the initial period, and then it's just going to be plus pi n. Because if I add n, if n is 1, then I'd get pi. If n is 2, I would get 2 pi. If n is 3, I would get 3 pi. If n was -1, I would still be at pi, right? Or I'm sorry, it'd still be, if n is -1, I'd be at negative pi. If n was -2, I'd be at -2 pi. But either way, we're hitting the intercepts on the x-axis. And again, we don't usually write it as 0 plus pi n. We can just write that as x equals pi n. Now let's go and take a look at this as the secant asymptote. So on the secant asymptote, we're looking at the x-coordinate, right? So we want to kind of know when is cosine going to be 0? So cosine is 0, you could see at the angle pi halves and at 3 pi halves. So when cosine is 0, that means the secant is going to be undefined because it's going to be 1 over 0. So the first smallest positive angle that we see where secant is an asymptote is x is equal to pi halves. And then the next angle where it's going to be undefined is at 3 pi halves. And then if we add another pi, that'll take us to 5 pi halves. And we can keep on going around in this kind of order or in the opposite direction. But either way, we keep on adding pi. To get to the next angle that's undefined for secant, we're just adding pi. So then that's why, again, we're going to write pi n. All right. So that is going to be our asymptotes. Now, when we're looking into identifying our range, I totally messed this one up. So let's go and take a look at these graphs. And this is very important because when we get to our examples, I'm going to be basing this a lot off of understanding the reciprocal functions as far as the sine and the cosine. So when looking at these graphs, you can see that the range is based off of what the range of cosecant is based off of what sine is, right? In this example of the parent graph, the range of sine is from -1 to 1. The cosecant graph is basically from -infinity all the way to the minimum of the sine graph, then from the maximum of the sine graph to infinity. And that's the same thing for cosine and secant, right? You can see that the domain or the range for cosine is from -1 to 1. Whereas the domain here is from -infinity to -1, and then from 1 to infinity. So when we have transformation, that's going to affect our graph. And actually, let's just write in the range here. So the range is going to be from -infinity to -1 included, union 1 to infinity. And the range here is going to be from -infinity to 1, -1, union 1 to infinity. So they have the same range. Obviously, their domain is going to be different because they have different asymptotes. Now, I'm not going to write in the domain. Well, actually, I might as well. The domain is basically all real numbers, except x cannot equal where the asymptotes occur, which in this case is pi n. And the domain here is basically going to be all real numbers such that x cannot equal, again, where our asymptotes are going to occur, which is pi halves plus pi n. Okay, but a lot of through my points, actually, I think I do cover that in some of those. So we'll get to that. We'll get to that in a second. But the main important thing as far as giving you something to follow for your range is basically it's going to be from -infinity to our -a, not determining like if a has a reflection or not, but -a plus our translation. And then union, our positive a plus our, why am I writing k again? I'm following what I previously did. Our vertical translation, if you guys remember, we used is d. So we're going to use d. So that's plus d, and then it'll be a plus d comma infinity. Now, if that looks like too many numbers for you, don't worry. I think once we get into our examples, that will make a lot more sense because we'll be able to look at the graph and kind of see how they're related. But for right now, we're just going to kind of leave this as the mathematical definition, and then we'll expand upon this further. So that's basically everything for cosecant and secant, where it comes from, how it's kind of derived, understanding these transformations, as well as understanding the asymptotes. So now what I'll do is I'll just kind of cover a quick little introduction of the cotangent function so we can expand upon that, and then we'll get into some examples.